Greetings, this is a continuation of acids and bases, and so we want to look at some of the properties and the calculations that are involved in acids and bases. So when you talk about polyprotic acids, then look at the word poly and then look at the word protic. Basically talk about the number of protons. So when you have more than one proton in an acid, then we call that a polyprotic acid. So if the difference between the Ka for the first dissociation and subsequent ones, the value is more than that, 10 power 3 or more, the pH generally depends only on the first dissociation. So what we are saying is, you know that the acid breaks down into a proton. So we'll have the first dissociation that gives us the first proton, and probably the second dissociation that gives us another proton. So that is what we are talking about, the first dissociation, which that will be Ke. Because it has more than one proton, it will break down into other more than one proton. So we have the first dissociation and then the subsequent Kas. So we are saying if the subsequent Ka value is 10 to the power 3 or more, then the pH will depend on this first dissociation. Okay, and so we have various polyprotic acids here. You can see that we have a possibility of having two protons there with Ka1 and Ka2. The same with carbonic acid. We have Ka1, Ka2, and then we come to the citric acid. We have 3 protons, and so it can dissociate 3 times and with those values. And the others are other examples of polyprotic acid. So when we now come to bases, the weak bases, remember we talked about strong and acids, strong bases and weak bases. So when a base reacts with water, it produces the hydroxide ion. So that is what you can be able to see. So an example here is ammonia plus water to give us the ammonium ion and the hydroxide ion. So you see that this NH3, it gains a proton to give us NH4 plus. And then the water here, okay, it loses a proton to give us the conjugate base. So our definition of acids and bases in terms of a proton, one gaining proton or losing a proton donor or proton acceptor, basically we can be able to see it through this reaction. Okay. So when you're looking at the equilibrium constant expression for the base, then we have this as our base, we have this as our water liquid, then we have the positive ion and then the hydroxide ion. So the equilibrium constants for this reaction is what you're having here, Kc. But now because you're talking about the base, then you talk of Kb, which is Kb is the base dissociation constant. And so we have this, which is aqueous, then divide by that. So that becomes our expression for Kb. So there are various Kb's for a number of reactions that we have, and we can be able to pick that from this table. From ammonium, the conjugate acid is ammonium ion, and then this is the equilibrium reaction, which you should be able to write in terms of dissolving this in water to give us the ammonium ion and then the hydroxide ion. So each of them, you see that is a reaction in water, being dissolved in water to give us the hydroxide ions. And these are the Kb values. So these are the Kb values for the bases that we have. So in our determination of pH for a case of basic solutions, an example here is given where you ask to calculate the pH of 0.15 molar solution of ammonia. Okay, so first you write your equation, ammonia, water, to give us ammonium ion plus hydroxide ion. Then you write our Kb expression where we have that, okay, and then we divide by the ammonia gas. And we are saying the Kb for this is 1.8 times 10 to the power negative 5. But remember, the question expects us to determine the pH of a 0.15 molar solution of ammonia. Okay, so how do we determine this concentration? So we use the ICE table, so that we have that equation. So we need for ammonia, we need for ammonium ion, and we need for hydroxide ion. So the initial concentration from our equation is 0.15 molar of ammonia. Initially we have 0 of ammonium and 0 of this. The change, the C which is not here, is the mole ratio here is 1 to 1 to 1. So the change here will be a minus X. The change here will be a plus X. It will increase by a factor X, and then here it will also increase by a factor X. So that here we have 0.15 minus X as the equilibrium concentration, and X, 0 plus X is X, 0 plus X is X. So here we are saying that because it's 0.15 is not, it's a low concentration, a change of X could be negligible. Okay, and that is why you can approximate it to be 0.15. So how big is X relative to 0.15? That is the main thing. If it is so small, then it will not affect 0.15 by a big margin. And so you can then approximate it like that. So we have our concentrations. We've determined the concentration, equilibrium concentration of this as X. The one for this is as X. This was 0.15 minus X. But we are saying X is so low so that we can just have 0.15. So our Kb expression will then be equal to X times X divided by 0.15. And that is what is equal to 1.8 times 10 to the power of negative 5. So if you are determining the value of X, then X will be 1.6 times 10 to the power of negative 3. So you actually see that this is a very low value. But that is the concentration of OH, concentration of ammonium, and concentration of, that's X is the concentration of ammonium and this. But remember, we are supposed to determine pH. But here we have OH. Okay? So what then are we supposed to do? So the concentration of OH is equal to 1.6 times 10 to the power of negative 3 molar. So we can get POH. Remember, we want to get pH, and there's a relationship between POH and pH, which is supposed to be 14. So it means we can get POH to enable us get pH. So POH is a negative log of concentration of H, which is this one. So if you calculate that, then you get a 2.80, and so pH then will be equal to the 14 here minus POH, which is 2.80, and that gives you 11.20 as its pH. Another example is also given there. You have 0.1 molar solution of caffeine, a weak organic base, has a pH of 11.3. Then you're asked to calculate the dissociation constant. Okay, so in this case you have pH. pH should help you to determine POH. Then after determining POH, then you're supposed to get the concentration of OH will be equivalent to X, and then from there we can now determine the dissociation constant. What are some of the factors that affect acid strength? One of them is the polarity of the HX bond. So this atom that is bonded to H, the polar this bond is, if there's a big difference in electronegativity in this, the more acidic the compound is. So basically what that means is if this has a very high electronegative value, then it will pull the electron cloud to itself, so it's easy to lose the hydrogen ion. So if it is more polar, then it becomes very acidic, because you can easily give up the proton, and that is what determines the acidity. So acidity increases from left to right, across a row, and from top to bottom. And this is because of the polarity of the bonds, and this is due to electronegative values of some of the atoms that are bonded to H. In oxyacids, okay, in which an OH is bonded to another atom Y, the more electronegative Y is, like in this case, chlorine, the more acidic the acid. So if HO is attached to an atom here, so if this has a high electronegative value, it means it pulls the electron cloud to itself, and so it is very easy to lose the hydrogen ion. So it makes it more acidic. So we have a series of oxyacids here, and the acidity increases with the number of oxygens. So the more the oxygens, the more the acidity. It makes it easy to lose the hydrogen ion, and that is what then determines the strength of the acid. Another one is resonance in the conjugate bases of carboxylic acid stabilizes the base and makes the conjugate acid more acidic. So the resonance, you can see that the movement or the change in position, the double bond resonates between here and here. So this resonance in the conjugate base, it stabilizes the base, and so it becomes then easy to lose the hydrogen ion. So this helps in making resonance then becomes a contributing factor in the acid strength by stabilizing the base. Okay. Then we have what we are calling Lewis acid. Remember we talked about Bronsted-Lowry acid, and now we are talking about Lewis. And we say that Lewis acids are defined as electron pair acceptors. So if we have our ammonia as base here with a lone pair, and then we have BF3 here, then this will donate a pair, and B accepts a pair of electrons. So an acid is this because it accepts a pair of electrons, and this becomes the base. So a compound with no hydrogens can still be a Lewis acid by basically looking at the movement of the electron, the pair of electrons. Atoms with an empty valence orbital can be Lewis acids, like when we talk of the D and F block elements. They have empty valence orbitals that can then accept the pair of electrons from the base, and so it makes them Lewis acids. Lewis bases, acids we've defined, so Lewis bases are defined as electron pair donors, as we've already seen. Another thing that is a Bronsted-Lowry base is also a Lewis base. So Bronsted-Lowry bases also have lone pairs of electrons. So if it is a Bronsted-Lowry base, then it is also a Lewis base. And Lewis bases can interact with things other than protons. So it does not necessarily mean a proton transfer or the one that accepts protons. In the Le Chatelier's principle in chemical equilibrium and how it affects the shift, the direction of movement. But in this case, I will want us to look at a solution and what their role is. So buffers are basically meant to control change in pH. Okay, you find them in hospitals, you find them in some places where you're supposed to maintain a given pH. So buffers are basically supposed to do that. So it's a weak conjugate acid base pair. So this is what it is made up of, a solution of a weak conjugate acid and base pair. So it is made up of both the acidic part and the base part. They are particularly resistant to pH changes even when strong acid or base is added. So it controls that pH change. So this is what happens. We have your buffer with an equal concentration of weak acid and its conjugate base. So it has this component and this component. Okay? So when you make it more acidic, then you see what happens. Okay? When you add more base, then you see what happens. If a small amount of hydroxide is added to an equimolar solution of HF, equal amount in sodium fluoride, for example, the HF reacts with the OH, to make F and water. Okay, so this is what you're having here. So OH plus HF gives us F plus water. pH change. If acid is added, the F fluoride ion reacts to form hydrogen fluoride and water. So that is how they are able to maintain and ensure there's no pH change. So buffers are very important in a number of reactions. So when you consider the equilibrium constant expression for the dissociation of a generic acid, this as an example, where we have this acid plus water to give us that. So Ka will be hydronium ion plus the anion here divided by the acid. When we rearrange this is what it becomes. Ka is equal to the ammonium ion, because it was this times this divided by this, so ammonium ion, anion, and then the acid. So when you take the negative log of both sides, so negative log of Ka, which is pKa, negative log of hydronium ion to the base of 10, which is pH, and then we have negative log of this divided by that. So you have the base and the acid. So we have pKa is equal to pH minus log concentration of base, concentration of acid. If you rearrange this, then we know that pH will be equal to, if you bring this side, then it is pKa plus log base acid concentration. And this is what we are calling the Anderson-Hasselbalch equation. Okay, so these are some calculations that are involved in buffer solution, because we have the acid and the base that help in regulating pH change. So an example here that I will want you to try is, what is the pH of a buffer that is 0.12 molar in lactic acid, this is the acid, and 0.1 molar in sodium lactate. Ka for lactic acid is given as 1.4 times 10 to the power of negative 4. So kindly work out this, and then you can send it at the end of the video. So our equation is given as that. As you try it, make sure this makes sense. So the pH range is the range of pH values over which a buffer system works effectively. pH range, the range of it, so it's a range that is compared to the performance of a buffer. Very, very important to take note of that. It is best to choose an acid with a pKa close to the desired pH, so that it gives you the pH range. What happens during your titrations? So a known concentration of base or acid is slowly added to a solution of acid or base. So that is what your burette. Then you're adding the base to an acid here as you monitor the change in pH or even color. So pH meter or indicators are used to determine when the solution has reached an equivalence point at which the stoichiometric amount of acid equals that of base. So when you talk of equivalence point, then we're talking about stoichiometric amounts, the amounts that react. So at which the stoichiometric amounts of acid equals that of base. So at that point, we have achieved an equivalent point. So from the, as you do your titration and you plot the graph, then what you have there, from the start of the titration to the near equivalence point, the pH goes up slowly. So it goes up slowly as you take the volume and the pH, And then just before and after the equivalence point, the pH increases rapidly. So it goes up, then it flattens, then as it increases, then it flattens again. So just before and after the equivalence point. So the equivalent point will then be at the center of this increase. At the equivalence point, moles of acid equals mole of base, and the solution contains only water and the salt, because it's an acid-base reaction, so we expect to have water and the salt from the cation of the base and the anion of the acid. So that is how we get our equivalence point. As more base is added, the increase in pH again levels off, and that is what happens there. So there's no change really. Unlike in the previous case, the conjugate base of the acid affects the pH when it is formed. So this is a titration of a weak acid and a strong base. So that is what you have there. The volume of the base, we have the pH, and we have the equivalence point, and the indicators that help guide us in determining the equivalent point. The pH at the equivalent point will be greater than 7 in this case. Phenolphthalein is commonly used as an indicator in this titration. Yes, very important for us to monitor the color changes. So those are some of the things that we need to be able to do when we're doing titration, determining equivalence point, the use of the indicators, and how that helps us to determine the equivalence point. The values that we get are for the pH and the volume of the base or acid that you use. So titration of a weak acid with a strong base, that is what we have there again. At each point below the equivalent point, the pH of the solution during titration is determined from the amounts of the acid and its conjugate base present at that particular time. So you look at the amount of acid and the conjugate base to help us in determining the equivalence point. When you have weak acids, the initial pH is higher and the pH changes near the equivalence points. This change is not very clear. They are more subtle. So we have our strong acid here, and then we have our Ka values that can easily indicate to us the strength of this acid. So still, when you're doing a titration of a weak base and a strong acid, the pH at the equivalent point in this titration is less than 7. So again, we have the volume of the acid, we have the pH, you plot that, and then you determine the equivalence point at that value that is below 7. Methyl red is the indicator of choice here, unlike the previous one which was using phenolphthalein. This one has methyl red as the most preferred indicator. So for polyprotic acids, we expect to have various equivalent points. You remember we said polyprotic are those that have more than one proton. So in these cases, there is an equivalence point for each dissociation. So as it breaks down this, you can see this is H3, it releases the first proton to give us H2, then H2 releases, gives us another proton to give us HP. So in each of the stages, then there's an equivalence point.